there, good morning. Welcome to another video lecture from Filipino Science Hub Ed. And today we're going to talk about electron configuration. My name is Ivy and I'm a chemistry teacher in Malayan Colleges, Laguna. And I also graduated from University of the Philippines, Las Bañas. And I am part of Filipino Science Hub Ed, who helps create modules for chemistry and physics teachers and students. So today we're going to talk about electron configuration. So the content standard is the quantum number mechanical description of atom and its electronic structure, and for MELTs, use quantum numbers to describe an electron in an atom. Draw an orbital diagram to represent the electronic configuration of atoms. So now, what is electron configuration? So the electron configuration is the standard notation used to describe the electronic structure of an atom. It describes how electrons are distributed in its atomic orbitals and follow a standard notation in which all electron-containing atomic subshells are placed in a sequence. So this is an example of electronic configuration of hydrogen and lithium. So what do we consider in writing electronic configuration? First, we must know the shell. So the maximum number of electrons that can be accommodated in a shell is based on the principal quantum number. And it is represented by the formula 2n raised to 2, where your n is the shell number. Shell n value and the maximum electrons in electron configuration. Here, I provided a table where you can check for the principal number, quantum number, and for the maximum electrons in electron configuration. So for K shell, you have n equal to 1. L shell, you have n equal to 2. M shell equal n equal to 3. N shell is n equal to 4. So for K shell, you have 2 electrons. L shell 8 electrons. M shell 18 electrons. And N shell is 32 electrons. Now, let's go to the subshell. So the subshell into which electrons are distributed are based on the azimuthal quantum number. This quantum number is dependent on the value of the principal quantum number n, and therefore n has a value 4, has 4 different subshells are possible. So when n is equal to 4, the subshells correspond to 0, 1, 2, and 3, and are named as S, P, D, and F subshells respectively. So the maximum number of electrons that can be accommodated by a subshell is given by the formula 2 times 2L plus 1. So therefore, the SPDF subshells can accommodate a maximum of 2, 6, 10, and 14 electrons respectively. So this is a table where we can see the principal quantum number value, the value of the azimuthal quantum number, and the resulting subshell in the electron configuration. Let's say, for example, you have n equal to 4. So the value for azimuthal quantum number is 0, 1, 2, and 3. And their resulting subshell in the electron configuration would be 4s, 4p, 4d, and 4p. All right. Now, let's consider one thing, the notation. So the electron configuration of an atom is written with the help of subshell labels. So this label contains the shell number given by the principal number and the subshell given by the azimuthal quantum number and the total number of electrons in the subshell in superscript. For example, if 2 electrons are filled with S subshell of the first shell, the resulting notation is 1s2. With the help of these subshell labels, the electron configuration of magnesium can be written as 1,2, 2s2, 2p6, and 3s2. So this is an example wherein we can see the principal quantum number, the orbital angular momentum quantum number, or as we know as azimuthal quantum number, and the number of electrons. So what principle do we follow in writing electronic configurations? First is the Aufbau principle. So the word Aufbau is a German for building up. So the Aufbau principle is called the building up principle, states that the electrons occupy orbitals in order of increasing energy. So the order of occupation is as follows. 2s is greater than 1s, 2p is greater than 2s, 3s is greater than 2p, 4s is greater than 3p, 3d is greater than 4s, and so on and so forth. So we have to use this order in order for us to get the electronic configuration of elements that we need to know. So we also use the Moduling's rule as a simple generalization which dictates in what order electrons should be filled in the orbitals. However, there are exceptions such as copper and chromium. Okay, now, so to understand the principle, let us consider the bromine atom, which has 35 electrons, can be found in period 4, group 7 of the periodic table. Again, we're going to consider this arrangement or order in order for us to know the electron configuration of bromine. So now, let's try. So you have here 35 electrons. Okay, so first we start at the lowest energy. So you have 1s. So the maximum number of electron for s is 2. So we place here 2. Then we have 2s, 2. Please take note of the number of maximum electrons for your azimuthal quantum number. So you have here 2p6, 3s2. So far we have 12 electrons. 3p6, 4s2. How many electrons do we have now? 10, 20 electrons. So let us continue. 3d10. So we have now 30 electrons. 4p. So what should be the number of electrons for 4p? So since we already have 30 electrons here, and bromine has 35 electrons, so we should write the remaining electrons, which is 5 electrons. All right, so I hope it's clear. Now let's proceed. So the second rule is the Hans rule, or the second principle, which is the Hans rule. So the Hans rule states that when electrons occupy the deuterated orbitals, they must first occupy the empty orbital before double occupying them. Furthermore, the most stable configuration results when the spins are parallel. So this is a visual representation of the Aufbau principle and Hans rule. Note that the filling of electrons in each orbital is arbitrary as long as the electrons are singly filled before having two electrons occupy the same orbital. So for the first diagram, it represents the correct filling of electrons for nitrogen atom. And the second diagram represents the incorrect filling of electrons for nitrogen atom. As we can see here, we have 7 electrons, and for the first diagram, there are parallel spin, and here there is an empty orbital. Okay, so we must follow the rule that we have to fill all the orbital before having two electrons occupying the same orbital. So this is the correct representation of filling of electrons for nitrogen atom. Lastly, we have to consider the Pauli exclusion principle. So Wolfgang Pauli postulated that each electron can be described with a unique set of 4 quantum numbers. Therefore, if 2 electrons occupy the same orbital, such as 3s orbital, and their spin must be paired. So you have there the same principal quantum number, the same orbital angular momentum quantum number, the same magnetic quantum number, but they have different spin magnetic quantum number. So let's try the following, right? Then abbreviated election configuration of the following. First, let's start with neon. So neon, using the Modulin's rule, we can start with knowing how many electrons does neon has. Okay, so for neon has 10 electrons because its atomic number is 10. Okay, so it has 10 electrons. Okay, so what else do we need to know? We have to do the electron configuration based on the arrangement of the energy levels. Okay, and using this one, we can easily identify how to write the electronic configuration of neon. So let's start with 1s. So again, the maximum number of electrons that S subshell can hold is 2, right? So we have to write here 2s. So again, the maximum number of electrons that the S subshell can hold is 2. And for 2p, so for p subshell, it can hold 6 electrons. So this is the electronic configuration for neon. So how do we write its orbital diagram? Okay, so let's say, for example, this is the orbital for 1s, and this is for 2s, and this is for 2p. Using Hans rule, again, we have to occupy first all the orbital before we write there you go. So this is the orbital representation of neon, and this is the electronic configuration. All right, so now let's proceed to another one. Okay, so how about carbon? So carbon, it has 6 electrons. Okay, so now let's start with carbon. So carbon, it has 6 electrons. Because the atomic number of carbon is 6, so we can say that it has 6 electrons. Again, we can use the Modulin's rule for the order of the energies, and also we can use this one in order for us to know what would be the electron configuration for carbon. Okay, so now let's start. So again, 1s1. So we have to put 2 electrons here. So this is the maximum number of electrons for S subshell. 2s2. So far we have 4 electrons. So how many electrons do we need to have 6 electrons? So of course we just need 2 electrons. So this is the electronic configuration for carbon. So now how do we write the orbital diagram using Hans rule? Okay, so again, we have to occupy first Okay, so again, we have to occupy first the lowest energy level before we proceed to another. Right, so this is the orbital diagram for carbon. I hope it's clear. Now let's proceed to another example. We have oxygen. So for oxygen, you have here 8 electrons because oxygen has an atomic number of 8. So we can say that oxygen has 8 electrons. Again, we can use the Maduling's rule, or maybe we could use the arrangement. So how about you try this? I will give you 5 seconds to answer. Okay, time's up. So now let's try to check your answers. So again, you need 8 electrons. So let's start with 1s, 2, 2s, 2. So how many electrons do we need? So since we already have 4 electrons, we need only 4 to make it 8. How do we write its orbital? So let's consider this. So again, before jumping to another orbital, we must fill in, or we must not, so dapat po hindi empty yung orbital natin. Okay? One, two, three, 4. Okay? So this is the electronic configuration for oxygen and the orbital diagram for oxygen. All right. So now let's proceed with this. Write the abbreviated electron configuration of the following. So we have following, the following elements are just the same with what we did earlier, but we are trying to find the abbreviated electronic configuration. So how do we do this? So let's say, for example, oxygen. How can we find the abbreviated configuration for oxygen? So the double gas configuration, or the abbreviated electron configuration, uses noble gas configuration, which has full electron shells, and to describe the electronic structure of your elements. So since oxygen has 8 electrons, so again, let us write here the atomic number of oxygen and how many electrons that does it has. All right, so oxygen has 8 electrons, and for its electronic configuration, you have 1, S2, 2, S2, and 2, P4. Okay, so again, from what we have read a while ago, the abbreviated electronic configuration is the noble gas notation. Okay, so the nearest noble gas for oxygen, and we have to consider the nearest noble gas for oxygen, and it must be below the number of electrons of your oxygen. So in this example, we can say that the noble gas that is near for the electrons, for the number of electrons of oxygen is helium, right? Because helium has 2 electrons, while neon has 10 electrons. So we have to consider the noble gas helium. So how do we write the abbreviated? So since we are considering the number of electrons of helium, it means that we have to replace 1s2 with helium. And then write the rest of the electronic configuration. So this is the abbreviated electronic configuration for oxygen. It's time for you to do the following. So please do the following: carbon, oxygen, potassium, and nitrogen. So this is an additional resources where you can see the atomic orbitals being occupied by electrons. You can use this by clicking the link below. So the electron configuration is a listing which atomic orbitals are occupied by electrons and how electrons are in each type of atomic orbital. So the ground state electron configuration is the lowest energy combination of electron in the atomic orbitals, and your task is to discover what ground state electron configurations are and how this can be predicted from the periodic table. Also, this is a supplementary video wherein you can write electronic configuration for an element in each block. So as we can see here, you have there the full electron configuration, the condensed electron configuration, and this can help you in writing the following. All right. So just click the link below for you to know how to write electronic configuration in each block. So here is the problem set for this topic. So you have to write the abbreviated electron configuration, which means that you don't have to consider the noble gas notation. Okay, so the answer is here also. And last one is you have to write the abbreviated electronic configuration of the following. And also I provide here some answer. And I think that's it for today. Thank you so much for your time in watching my lecture video. Bye-bye.